Hello everyone, let's get started. In last video, we discussed how to calculate the rotation matrix, any general case. So I told you in every case, you have to just find the corresponding angles. That means bar and unbar vectors angles, right? If you find the angles, then you can calculate the rotation matrix. Okay, any complicated case. So today, what we are going to discuss here, we are going to discuss the transformation rule of the tensor. You remember in some of the in some of the part of my discussion, I would have pointed out briefly, all metrics are not a tensor. So these statements I have given here and there when I am explaining something. So today in this video, we are going to study what is the reason behind that? What is actually the physical meaning of the tensor, right? Okay. What is the difference between matrix and tensor? Those things we are going to study here. Okay. So before starting that, so let me prove one of the findings we talk about, right? That means the vector, when we derive the vector, the transformation and bar and unbar coordinate system. So I told you the vector itself, it's remain unchanged, right? So only thing we change the vector components, right? For example, in this case, if you consider a vector, vector is same in both coordinate axes. Only thing we consider the different components when you represent in the different coordinate system. If the vector is same, the magnitude of the vector is must be same for both coordinate system, right? Can we prove this? That's what we are going to discuss, right? So for this, let me uh, refresh the what we have discussed regarding the uh, magnitude of the vector. If we want to find the magnitude of the vector, so this is, you can find this one actually the dot product between the vector itself, right? So that means this is, you can write AI, right? Okay, so this is already we discussed, right? Okay. So this one I'm going to use it here. Let's say my unbar, that means let's say bar coordinate, right? Bar coordinate system, the magnitude of the vector, right? I'll take scared, right? Okay. So if it is magnitude, actually I have to take square root, right? Okay. So let me take this square. How can I write based on this definition, right? I can write V bar I index notation. Similarly, V bar I, right? Okay. So now what I'm going to do, I'm going to apply our transformation rule. Your transformation rule you could remember, right? So that means this is the transformation rule, right? V bar rotation matrix into V, right? Okay. So now I know V bar. Now I'm going to transfer uh, unbar coordinate system. That means V bar is actually rotation matrix into bar vector rotation matrix into unbar vector, right? So this is the bar vector. I'm going to apply the rotation matrix. So when I am writing the rotation matrix, I have to be very careful the matrix notation, right? For example, let's say if I want to write this VI, so let's say I will write VI bar. So when I write VI bar here, so how can I write here? So I can write R. Then you remember, right? The second subscript of the matrix and subscript of the vector must be same. It should be repeated index, right? Vj and Vj. This is something we discussed in our previous videos, right? Okay. Rij, Vj. Both side now free index is I. So now I'm going to use the same thing here, right? Ri, J, and Vj. Okay, right. So now again I'm going to use for the second vector, right? Second Vi. Second Vi, I cannot use J now because if I use J, J repeats more than 2. It is against our rule. Therefore, I'll keep I, right? I can write I because I only 2 times. Instead of J, I will write K, right? Okay. So I hope this is you don't have any problem here. Just I am following this one, right? Okay. Right. So now let's say this is just a number, then Vj I can take it this side. I will combine Rij and Rik, right? Okay. Then Vj, Vk. Now when you multiply two matrix, right? So you know the matrix multiplication rule. It must be the second subscript of the first matrix and first subscript of the second matrix must be same. Here is not same, right? So therefore, you have to make it transform, right? If you write it Ji, it is actually transform, right? So this is also we discussed in a previous video, right? Ik, Vj, Vk. Now, this is, right? Transpose into rotation matrix. You know our rotation matrix transpose and inverse is same. Okay, I will write it one more step for your understanding, right? Inverse, because this is the orthogonal matrix, Vj, Vk. Then matrix into transform. So that is our Kronecker delta, right? Okay. So how can you write Kronecker delta? The same indices you have to remove. Then, because this is repeated index, right? When you substitute with the one quantity, same free index you have to use, right? J and K free index, right? Jk. So now Vj into Vk, right? So now what I am going to do, I'm going to apply the properties of Kronecker delta. What is the properties of Kronecker delta? This common indices you have to cancel, then replace with that one, right? So therefore you will get Vk, Vk. What is this Vk, Vk? Ai, the magnitude of the vector, right? So now magnitude of V vector scared, right? You see what we have proved here, that means bar vector magnitude equal unbar vector magnitude, right? So this is something we discussed, right? The vector magnitude is invariant with respect to the coordinate transformation, right? Okay. So I hope this is clear for everybody. If you have any problem, just let me know in the comment section, right? Okay. Right. In this next video, what we are going to discuss here, the transformation rule of tensor, right? For tensor, right? Transformation rules for tensor, right? Okay. For tensor. Okay. So far, what we have discussed, let me write that one, right? So let's say you want to find bar vector, that is transformation matrix, that means rotation transformation matrix into unbar vector, right? So if you want to write it in a index notation, I, so therefore here Rij, Vj, right? Okay. So this is our index notation, right? Okay. So what is your Rij actually? This is actually the first one for bar vector, right? So Ei for bar vector dot product with Ej. unbar vector, right? So this is your rotation matrix, right? Okay. Then also you know this one, right? Uh, that means rotation matrix R transpose, okay? Or R transpose into R is identity matrix, right? Okay. So these things you know already, right? This one, right? If you can transform one vector using a transformation matrix into another vector, this is called, if any vector is obey this transformation rule, this is called tensor rank 1, right? This is the rule, transformation rule for tensor rank 1. Okay. If you take all the vector, any vector, it will follow this transformation except the vector 0, right? 0 vector is invariant. So if you transform into a new coordinate system, still it will be 0, right? So normally 0 vector, it is like a trivial vector, trivial solution in most of the cases. We don't care about 0 vector. So all the other vectors, it follow this transformation rule. If any vector follow this transformation rule, that we define as a tensor rank 1. When I say tensor rank 1, it must follow this transformation rule. So this is the rule for vector. Okay. So now we are going to discuss the rule for second order tensor. So based on that, we can extend our discussion for any number of order, right? So first discuss second order tensor. So for this, again, I am telling you all the vector, right? It follows the transformation rule, right? Okay. So now I'm going to take one vector, right? Consider a matrix. Consider a matrix. Okay. So let me check which notation I use. I have taken as M, right? I will use the same, right? Okay. M. If I write index notation, it is actually Mij, right? So this matrix which relates, right? Let's say two vectors, right? Relates two vectors. U and V, okay? In this way, for example, your V matrix M into U matrix, right? Okay. This is a matrix, right? Again, don't confuse this matrix M with the rotation matrix. Rotation matrix, you are changing the coordinate. Now, I define a matrix which relates two vector in one particular coordinate system, right? So both vectors are now unbar coordinate system. This matrix, it's connect both vectors, right? Matrix is a transformation. You can connect two vectors to, right? Two vectors using the matrix, right? Because matrix into vector, it is actually uh, a vector, right? Okay, we already discussed this one, right? Okay. So now this is the first one, right? So let's say equation number 1. Okay. So now I'm going to consider now the similar way uh, two vectors, right? Let's consider two vectors. Okay. Uh, that means let's consider a vector V. Now I am considering vector V rotated, that means in rotated coordinate system, right? Okay. So that means in rotated coordinate system, in rotated coordinate system means my vector u now become bar coordinate system, right? U bar. Similarly, my vector v now become v bar, right? So then my matrix M in rotated coordinate system, it will be M bar, right? Okay. Now, if I use transformation rule for the vector in my rotated coordinate systems, I can write V bar, it is M bar into U bar, right? So this is our equation number 2, right? Okay. So now what I am going to do, I'm going to find the relationship between M and M bar. Then I can find the transformation rule, right? But previous transformation rule only for the vector, right? Now I'm going to find the transformation rule for the tensor, right? That means matrix. Okay. Right. So now let's say which method we will use. Uh, we can use any method, right? We can use index notation or normal one. Let me use the normal one, right? Okay. So if you want, I can explain index notation also. No issue. Both are simple, right? Um, okay. Or else, what shall we do? Okay, we will do any of thing, right? Rather than wasting our time. Okay. From equation number 2, uh, okay, let me take equation number 1, right? Equation number 1, it's bar vector in this one, right? Okay. Previously, we discussed bar, if you want to find unbar vector with respect to bar vector, you know, transformation of R, transform of R, then V bar, right? So this is already we discussed, right? So you remember this equation, right? I think, yeah, this equation, right? Yeah. Yeah, first equation, right? Okay. So the same equation I'm going to use here, right? So instead of V bar, okay, first equation, right? V, I will write R transform into V bar, right? Equal, uh, I'll keep M same, right? M, okay, M, U, instead of U, I will apply again the transformation rule, right? That means rotation matrix into uh, U bar, right? Okay, right. So now what I'm going to do, I want to calculate V bar here, right? So therefore, I have to multiply by inverse, right? That means you must remember this. Don't forget. Okay. So this is equal, right? So actually already inverse is there. I will write one more steps then. R inverse V bar M R inverse bar, right? Already inverse is there. Now you have to multiply by R in both sides, right? So when you multiply R, okay, I will write it. So I will write it in different color. That means I am multiplying here rotation matrix R in both sides, right? Okay, pre-multiplication. Now it will become identity matrix. You will get V bar here. Then here matrix rotation matrix R. M R inverse actually R transpose, right? I will write is R transpose here. U bar, right? Okay. So this is your now equation number 3, right? Now you can compare equation 2 and 3, right? If we compare equation 2 and 3, so what you can find? This matrix actually your bar matrix, right? So that means my M bar now R M rotation matrix, right? Transpose. Similarly, you can find M, right? So that means if you multiply R inverse here, R here, right? So that means R inverse is actually R transpose, M bar, R, right? Okay. So this is the transformation rule for matrix, right? If any matrix, it obey this transformation rule that we define as a second order tensor. This is the second order tensor rule, right? If any matrix, if it obeys this transformation rule, that we define as a second order tensor. If it is not defined, that is not a second order tensor. So for example, if you consider the identity matrix, this is the isotropic matrix, right? It is isotropic matrix. It doesn't change with uh, transformation rule, right? That means we even if you rotate, you will get same I matrix, right? So this is invariant. Okay, it is an invariant. Uh, Invariant with respect to the orthogonal coordinate transformation, right? Okay, so this is called the isotropic tensor, right? Isotropic second order tensor, right? Okay, it's an isotropic matrix, right? Okay. Right. So now we are going to generalize for any coordinate system, right? Uh, okay. Before that, let me derive this one, right? That means, so what I have to derive bar coordinate system, right? That means delta ij bar, right? This one is same as delta ij, right? That means what I have to prove here, I bar equal I, right? So this is what I am trying to prove because it is isotropic matrix. Okay, I'm going to use this transformation matrix, right? If I want to find uh, this one, I can write it this way, right? So that means first equation, right? Bar with respect to unbar. Here I will get rotation matrix, then unbar matrix, then R, right? Okay. So now I have to put my notation, right? Okay. So here I and J how can I say? This is my uh, rules, right? Transformation rule, right? Okay. Before going to this one, okay, I will explain here and come to here, right? So that means here, if I want to write M, let's say M I J bar, right? Okay. So same free index must be here, right? I am writing the first one, right? R I K, then M here, R J, right? because I used free index. Here I have to use another this one L, right? Then K and L must be repeated index, right? K. So this is the index notation for this one, right? For example, if you want to write the second case, Mij, it is R uh, R I K, right? Uh, Here transpose, right? We must put this transpose here, right? So here RIK transpose M bar KL RLJ, right? Okay. Okay. Right. So you can use any both side, right? Okay. So I will do one more thing here, right? So let me bring this one down. Okay. Here I'll keep RIK, then MKL. So this one, because of the transpose, just I can change the index, right? JL. So normally we write this way, right? Okay. So let me bring this one further down. Okay. So normally what we are doing, just we write the R first, RKIK, then RJL, right? Then MKL. So this is the easiest way to remember this one, how to apply this transformation rule for the matrix, right? Okay. First, this I, you will write here one R matrix. This J, you will write another R matrix with a first subscription, right? Then put one, what is that? Uh, Repeated index. Then these two repeated indexes, you will put the matrix, the given matrix, right? Okay. So I'm going to use the same idea here, right? First, I will write R matrix for this one, the second R matrix with J. Then I will put KL here. Then my unbar matrix KNL, right? Okay, that's all. So now you can see I'm going to apply the rule here, right? Uh, Chronicle delta property, right? The same index I have to remove, replace that one with another index of chronicle delta K, right? So that means RIK, right? RIK, RJ, now K, right? Right. Now, again, what is this one? It is matrix multiplication, right? RIK, RJK, but you have to transpose, right? Because it is not following the matrix multiplication rule, right? The last digit and first digit must be same, right? RK, this will be KJ transpose, right? This is, R into R transpose, again, identity matrix, right? Delta, K cancel out, free index, right? IJ. You see, delta ij bar and delta ij equal. So that is what this is a isotropic matrix, right? Okay, right. So next one we have to discuss the third one, any nth order matrix, right? Nth rank tensor. Second order tensor or nth order tensor, right? Okay. Now, so that means here, if I want to write any, let me bring the previous one, right? The previous one, right? M bar, ij, it is R, the first one, right? Then second one, J, here, K, L, M, K, L, right? This is way we have written, right? So now what I'm going to do, I'm going to write any nth order, right? Nth order mean you have to have n free index, right? So that means I, J, K. So like that. Okay, I will write it like this, right? I, J, K. That means n free index bar, right? So how can I write here? First, I have to write the R matrix, right? R, I. Then second R, J. So like that, R, K first. Then second subscript, right? P, Q. Let's say this is my R, right? Okay, R matrix. Now I have to write this one, right? Unbar. A. Unbar, what is the index? I have to pick the second one, right? P, Q, dot, dot, R, right? So this is the transformation rule for any rank tensor, right? Okay. So that means whichever tensor follow this transformation rule, we define that one as a second, that means tensor, right? Okay. I think this video bit extended, no issue, because we have discussed very important stuffs. Uh, at the last, to end this video, let me define the trace of the matrix, right? Trace of matrix. Let's take matrix Mij, right? So that means trace of the matrix we marked as like this, right? Tr matrix M, right? So in other word, trace matrix Mij, right? Okay. So what we define as a trace matrix, let's say matrix M is this one, right? M11, M12, M13, M21, M22, M23, M31, M32, M33, right? Okay, right. What we define as a trace of matrix, actually the diagonal, right? The summation of the diagonal, right? That means M11, M22, M33. So if we want to represent in index notation, we studied already the summation convention, repeated index, MII. This is actually the trace of the matrix, right? This trace of the matrix, so this is actually MII, right? This trace of the matrix also independent with coordinate system. So for example, let me take trace of M bar matrix, right? So based on the index notation, you can say this is M bar matrix II, right? In the bar coordinate system. So now if you want to convert this one into unbar coordinate system, I have to use this transformation rule, right? So let me use the transformation rule R first subscript, second R matrix, first subscript. Both is I, right? So here K, this is L. So now I will write here MKL, right? Okay. Now again, this is, we already discussed delta, right? The previously just now we can write this one as a transpose, again delta, right? So delta, this is common index. If we cancel out KL, this is MKL, right? So now apply delta property, select one index, right? K is a common, then you can write MLL, right? What is MLL? L is a free index, right? You can write MII, no problem, right? This is actually MII because this is the dummy index, right? You can replace with anything. So now this is actually trace of matrix M, right? So what we have proved here, the trace also independent with transformation, right? Transformation rule. Okay. Yes. Okay, no issue, right? This video bit extended video, but no issue. We discuss very important things, very important things, right? Out of the video what we have discussed so far, if I rank the importance of the video, this part I will put as a number one, right? So very important one. Try to understand and try to practice. Then how to write this one is a index notation, right? Okay. See you on next video. Uh, Subscribe and like and share among your circle, right?